Hello and welcome to this presentation on DirectX11 Billboards and Particle Systems. To start out, we're looking at something that's maybe a little bit familiar, but it's slightly different. We have a pyramid with a texture on it, and we have just a rectangle with the penguin guy on it, and that rectangle has some transparency. The rectangle is actually made as what we call a billboard, and this is a rectangle that always faces the camera, so I have a side-to-side movement capability added in here, and as I move to the side you might be able to notice that the penguin rotates a little bit so that he's always facing the camera or facing the viewer. And they refer to this capability as a billboard. Notice that the pyramid, we're able to see the different sides of the pyramid, but we never see the side of the penguin. We're always seeing the penguin facing us, this billboard facing us. And this has some interesting uses in things that are fairly far away in games. So for example, if you have foliage like trees and bushes, maybe rocks that are fairly far away, instead of rendering a bunch of polygons for those trees or items, you can render just a billboard with transparency that's always facing the camera, and you've only rendered 2 polygons. So this can generate some significant savings. It's typically just used for things off in the distance. It doesn't look quite as well when you get up close to it. As the camera comes close to an object like that, it's likely that you would replace it with a real tree or a real rock, hopefully in a seamless type transition. How do we get this effect, this billboard capability? First thing, we'll look at some math. You'll see that there is a rectangle here made up of 4 vertices, P0, P1, P2, and P3. And we're going to define 3 vectors for this billboard. One is called a look vector or a forward vector. So this is the vector that always faces the user. And all we have to do to calculate this is take the billboard position and subtract that from wherever the camera or the viewer is. So we take the camera position minus the billboard position, and we have this look direction, or this forward direction, the direction we want the billboard to always face. Next, we compute or get an up vector, and because we want the billboard to be oriented with the camera, we just set that equal to the same up direction as the camera. The last one that we need is either a left or a right. In this case, I'm creating a right vector. So what direction is horizontal or to the right in the billboard's perspective? Well, we can just use a cross product for that, and because we're using a left-handed coordinate system, we'll do the cross product of the up vector with the look vector in that order, and that'll get us a vector to the right. Of course, we want to make sure these are normalized, so the up vector and the right vector, we want them to be normalized so that they have a length of 1. Once we have that, we have the billboard position. We assume we know where we want the billboard to be. We use the billboard position and the camera position and the camera up direction to compute up and right vectors for the billboard, and we normalize them. Then the other piece of information we want is the width and height of the billboard. How wide do we want it? How high do we want it in world coordinates? Once we have that information, we can compute P0 as the billboard position plus the right vector scaled by width over 2, and then plus the up vector scaled by height over 2. And similarly, we can compute P1 and P2 and P3. So now we have the four corners of our billboard. We can do this on the CPU, but it turns out we can also do this in a geometry shader. So the changes that we'll have in our code is we're going to add or modify the vertex type and input layout to have a position and a size variable. So we need the width and height if we want the billboards to be different sizes. So that means we have to modify the input layout, modify the shader, the constant buffer, the sample state, we need that for the texture map, and the blend state, we need that for the transparency. So because this billboard is different, I'm going to push all that information from what was in the application class. I'm going to push all that to the object class. The nice thing is that each billboard only needs its own position in world coordinates, and it'll be the job of the geometry shader to compute the four vertices and the two triangles for the billboard. So for the geometry shader, we need to set constant data to make sure it includes the camera position and the camera up direction. And only a single vertex gets sent to the geometry shader. And the geometry shader is going to produce four vertices to form what's referred to as a triangle strip. So up until now, we have seen triangle lists. And a triangle list is a list of at least three vertices, or a number of vertices, and an index buffer where every three indices in the index buffer define a vertex, a triangle. The geometry shader has the capability to produce what's called a triangle strip, and this has some efficiency advantages. So we can send three vertices from the geometry shader to the pixel shader, and it'll render a triangle for us. It'll interpolate and render a triangle. A triangle strip, if we add a fourth vertex, then it will actually render two triangles. And this is the way it's done. What happens is the first three vertices produce the triangle 0, 1, 2. Then the next vertex that's added produces a whole other triangle using the previous two vertices. So if I send 0, 1, 2, I get a triangle 0, 1, 2, and then if the 3 is added onto that, a fourth vertex is added onto that, I get an entire additional triangle using the previous two vertices plus the additional one that's been added. So this is a little bit of efficiency feature where if your geometry lends itself to being placed in what's referred to as a triangle strip, where you can just add on an additional vertex and define another triangle based on that one you added plus the previous two, then you can take advantage of this triangle strip. So we'll see some more details on the geometry shader in just a minute. One additional feature or requirement of the geometry shader is that it has a primitive ID. This is just a number, just an index identifier that says, okay, this is triangle 0, this is triangle 1, this is triangle 2, and that's a requirement that the geometry shader takes and must pass along. Before we get to the particle system, let's take a look at the code changes for the billboard. I actually put the billboard demo in what we refer to as particle system module, and actually call it a particle system, but it's, in this particular case, it's really just a billboard. So what happens is that for a particle system, we just make a bunch of really small billboards with transparency that move around and put a transparent texture on them, and we call those particles. But it's essentially a bunch of little billboards. So it may be a little bit confusing in that even though this is called particle system, it's really demonstrating billboard capability at the moment. So the particle vertex just has position and size, and the single position is going to be expanded to 4 positions, and the texture coordinates are also going to be added by the geometry shader. We've got particle update data to include velocity and lifetime. We're not using this right now because we're just using just creating a billboard. Here's the geometry shader constant data. So this is the data we're going to send in to the geometry shader. We need the view projection matrix to transform coordinates into from world space into homogeneous clip space or screen space. And we also need the camera position and the camera up vector in order to create the 4 vertices on the billboard. So this is should be pretty familiar. We've got a vertex list, the particle data list, which allows us to do updates on particle systems. Is not going to be used right now. We've got texture, we've got input layout, we have shaders for vertex shader, geometry shader, and pixel shader, and we've got geometry shader data passed in through a constant buffer. We have a sampler state and a blend state. All of this should be familiar. And the reason we push this into the particle system class or this billboard class is because the sampler state might be the same as what we're rendering for the pyramid, but the blend state will include transparency, whereas the pyramid may not want to include transparency. And the shaders for the billboard will definitely be different than what we use for the pyramid and some of our other objects. So we want, in order for these to be unique, we push them down into the particle system class. There might be better ways to design this, where you might have a shader manager that maintains a list of different shaders and constant buffer data, and you swap them in and out. But here we just pushed it down into the billboard or particle system class. When we go to initialize, we initialize the shader file name and the texture file name, and we push back just one single vertex. So I just have one billboard, so I just push back one single vertex, and it's at 0, 15, 0, and I've got it sized at 20 wide by 10 high. We can change that. When we go to create the DirectX objects, we create the vertex buffer. Again, it's just one vertex, but it's of type particle vertex. It just has a size and a position and a size. We create the constant buffer, and it's using the type defined in the particle system module. So it has geometry shader constant data. We create a sampler, and this could probably be reused. This is probably the same as the pyramid. I don't know that there's any changes here. The blend state is what we've seen with, set blend to true and use the 1 minus source alpha blend operation. So this is what we've seen in the transparency capability we've already looked at. We want to initialize the shaders. So in this case, we actually have 3. We have the vertex shader, we've got the geometry shader, and we've got the pixel shader. And notice that the geometry shader creates a geometry shader type program. We put those into actual shader objects, and we also create the input layout to include an XYZ. And here we went we made one other important change here. Eventually this single billboard is going to be used to create a bunch of small particles, and the physics update on those particles we're going to do on the CPU. So I wanted to try to take advantage of the operations, the SIMD operations on the CPU, to see if we can get some performance improvements. So instead of using a three-dimensional vector, we're actually using the XM vector, which is a 4D vector that's mapped to those special floating point registers that provide access to the SIMD instructions like SSC and so on. So this is actually now a four-dimensional position vector. We're not going to use the W value, but hopefully by using this and using these SIMD instructions on the CPU, we may get some performance improvements. So when we create the element descriptor, the position now is no longer a 3-channel float, but it's actually a 4-channel float. So you see R32, G32, B32, A32. The size is just a 2-channel float that gives us width and height. So that's the input layout. The texture, as you've seen in the texture demo, we are using the DirectX toolkit to load the Windows imaging component as a texture map from a file. When we're done with all this, we can release the shader blobs. For the render, we set the shaders because it's going to be different from the shader that we use for the billboard. Is going to be different than the shader that we use for the pyramid. We update the constant buffer and send that to the geometry shader, and we send the texture to the pixel shader. We set the blend state, set the input layout, and draw. Set the vertex buffer and draw. What does the shader look like? The shader for the pyramid is what we've seen before. We pass in the worldview projection matrix. The vertex shader does the transformation to homogeneous space. The pixel shader looks up the texture color in the texture using a particular sampler. So nothing really new there. Same as typical texture mapped polygons. In the particle shader, we'll see some differences. This constant shader data is just the view projection matrix, because we're going to assume that the billboard or the particles are already in world coordinates. So we just need to multiply by the view and the projection matrix to put them into homogeneous screen coordinates. Camera position and camera up, those are also four-dimensional vectors, so that we can use the DirectX math to vector addition, subtraction, cross product, and so on. Here's the texture that's used, here's the sampler that's used, here's the vertex in. Remember that this world position is a float 4. We're using the SIMD registers that are 128 bits or 4 floats wide, and the size in world space is a float 2. The vertex out is exactly the same. So the vertex shader really isn't doing anything. It's just passing the information along to the geometry shader. The output of the geometry shader is a four-dimensional float in screen view coordinates, a 2-dimensional texture, and this unsigned integer primitive ID. So that's something that's new and a requirement for geometry shaders. On the geometry shader itself, we have this prefix here where we can specify a maximum vertex count, and having that as small as possible can increase performance. And I think there's a limit to the number of vertices that the geometry shader can output. I don't recall what that limit is, but I think there's a limit to it. We know that our billboard's just going to have 4, so we're just going to say that the max vertex count is 4. We're passing in a vertex out here. So here we're passing in an array of just one vertex out type that's a point, and we're passing in this primitive ID, gets passed into the geometry shader, and we're outputting a triangle stream of type geometry out, which is this right here. So this syntax is a little bit different. We've got this point here that's required, we've got this max vertex count, we've got this primitive ID, and the output is this triangle stream of this structure type, so it's a little bit different. This is the math that we saw before, where we normalize the up vector, compute the look vector as the camera position XYZ minus the billboard position XYZ, normalize that, take the cross product of the two to get the right vector, and then compute the half width and the half height as the vertex size data that's coming in divided by 2 or times 0.5. Take the position of the billboard and subtract the right times the half and add the height, the half height times up, extend that to 4 dimensions and multiply it by the view projection matrix, and we get the homogeneous position. The texture, we're going to make 0, 0 for the top left here. Give it the primitive ID and output. Append it to the triangle stream. And we do something very similar for the top right. And I guess these comments are wrong. This is probably the bottom. It looks like this might be the bottom left and this might be the bottom right on these last two. And that's the end of the geometry shader. So we've just appended 4 vertices to the stream, and because it's a triangle strip, we're going to end up getting 2 triangles out of those 4 vertices. The pixel shader is pretty simple. It has everything it needs to just look up the color and the texture using the particular sampler and just return that color. So the real bulk of the work here is done, for the billboard anyway, is done in the geometry shader. In the main application, we include the DirectX toolkit for loading, we include the particle system, we define a particle system, and again, this is really a billboard. It's not a particle system, it's really a billboard. We initialize the particle system by setting the shader file that we want to use and the texture that we want to use, and we create the DirectX objects for that. And then when we go to render, here we're setting the shader objects for the pyramid, And note that we don't want to use the geometry shader, so we set it to null. The pyramid's not using a geometry shader, so we set it to null. We set the blend state, we set the input layout for the pyramid, and then draw the pyramid. Then when we go to draw the particle system, in that render function we saw that it's set different shaders, different input layout, different blend state, different sample state, and drew our billboard. So those are the changes that we see. And here's the billboard example. Starts out a wireframe, and we can see that the penguin guy is always facing us. So again, we can modify this billboard. We can use the billboard for a variety of purposes, but one modification we can make to the billboard is to use it to create a particle system. And in a particle system, we're going to create a bunch of really small billboards, thousands of them, send them all to the shader and have the shader draw them for them. And on the billboard, we'll put a small, somewhat transparent texture for smoke or fire or whatever it is that we like. And basically, each particle in the list is going to have a position and a width and height, so we can adjust the size if we need to. It's also going to have a separate piece of data for velocity and lifetime. So if we look at the code for the particle system, we see that there's a separate structure of data for the particle's velocity and lifetime. So we're going to have a separate list. It's going to be the same size as the vertex list. It's going to have the velocity and the lifetime of this particular particle. We also have some information on how the particles are going to be spawned or emitted. And so we have an emitter position. We have a maximum number of particles that we want to spawn, we're going to have total. We have a minimum and maximum spawn that we're going to do each update. We have a minimum maximum speed that they're going to be emitted with, and we have a minimum and maximum lifetime. It's a nice touch when a particle lasts, maybe just a few seconds and dissipates. We can add an acceleration, so the particles may be either accelerating or decelerating due to wind or drag or gravity or some other effect. And then we have this thing called an emitter offset and emitter radius. So there's a variety of different ways to spawn or emit particles, but one way I found useful is to define an emitter position, an emitter offset, which is also a vector, a displacement vector to some other location, and then an emitter radius. So the emitter position is just a point, the offset is a vector to some other location, and then the emitter radius defines a sphere. So what ends up happening is we spawn new particles at the emitter position and give them a velocity that is equal to some random value in this emitter radius sphere, some random location. That's the direction. We normalize that, scale it by some random value in our velocity range, and then that is the direction, the velocity vector for the particle. So really we can create almost like a cone of particles, or if this emitter offset becomes 0, then the emitter radius sphere surrounds the emitter position and the particles randomly spawn in all directions. If we make the emitter radius really small, imagine if the emitter radius were actually 0, then we would get a line of particles emitting. So we have a lot of variation that we can use this particular geometry for in spawning particles. On every update, we do an algorithm that's something like this. For every particle, and let's say we might have 1,000 of them, If the particle's lifetime is greater than 0, meaning it's alive, then we just do a physics update. And if you've taken the physics class, these equations may look similar for you. We update the velocity by the acceleration times delta time, and we update the position by velocity times delta time, and then decrement the lifetime by delta time. If the particle's lifetime is not greater than 0, which means it's dead or it's not being used right now, maybe we want to spawn this particle. And so we have pre-calculated a number of particles that we want to spawn this frame. And usually that's a random value between some range. And let's say maybe we want to spawn 100 particles this frame. Then what we do is we initialize the position, velocity, and lifetime of that particle and decrement the number to spawn, so that once this frame we've spawned 100 new particles, then we'll not do any more. And remember that the position and velocity of the particle are going to be defined by this: the emitter position, the emitter offset, and a random value within this emitter radius sphere. If we've already spawned enough this frame, and maybe there's 3,000 particles left over, that there's 3,000 that are not alive anymore, but we've already spawned enough, then we don't need this particular particle right now, and so we kind of hide it. We just put it infinitely far out on the scene and set its velocity to 0, so it won't be part of the scene. So let's take a look at what it looks like, and we can try out different values. So here's my particles being emitted from the top of the pyramid. And in wireframe mode, it's tough to tell that those are just really small billboards with a transparent texture on them. And there's a kind of a wind that's blowing to the right that's making the particles being pushed off, and you see they have a lifetime of just a few seconds, I guess, from when they're spawned to they seem to die out over here. So the lifetime is just a few seconds. Let's look at the initialization for some of these values. So I have a maximum value of 10,000, and you'll want to take a look at your frame rate. You want to watch your frame rate, because processing 10,000 particles on the CPU every frame can be a little bit computationally expensive. So you want to watch out. You want to watch your frame rate and be careful what value you use here. We have an initial position that's somewhere near the top of the pyramid. I'm spawning anywhere between 0 and 100 particles every update, every frame, with a minimum maximum speed of 1 to 5, a lifetime from 2 to 4 seconds, and a acceleration that is +1 in the x direction and -0.1 in the y direction. So they kind of slow down a little bit because the emitter offset is straight up in the air, +20, a y value of 20. So they're being emitted straight up in the air and kind of blown to the right with an acceleration that goes to the right, and slowed down a little bit as they go up, and an emitter radius of 3. So as I said, if we reduce this emitter radius to something really small, then in fact this is infinitely small, right? This emitter sphere now goes down to a point. Then we're going to be emitting particles in a line. And you see how the particles are being shot straight up, but they're still affected by this wind that we've got in there. But you'll see now that it's almost like a sheet of, almost like a plane of particles moving around. Something else that we could do is we could put the radius back to 4 or 5 doesn't matter in this case, and we can move the offset to 0. So what this means then is that this emitter offset is now 0, so this emitter radius surrounds the position, and when we get a random value in this emitter radius, it'll start from the center and just shoot out random value in any direction in that sphere. We can remove the wind and the deceleration, and you should just see a spherical cloud of particles coming out from near the top of that pyramid. So you see how they're being emitted and shot out in all directions. Somewhat equally and randomly. And notice that we've taken a substantial hit to the frame rate. So I haven't done a whole lot of work on trying to optimize this. We may be able to push some of the physics calculations out to the GPU, or perhaps only send those particles that are alive to the GPU rather than sending all of them. There may be some optimizations that we could do to improve performance, but this is the basics of how you would create a particle system out of a bunch of really small billboards. So this concludes this presentation on creating billboards and particle system in DirectX 11.